Matter lies. It tells you it's solid, that the chair beneath you will hold, that the ground won't vanish, that the hand you raise is a real thing in a real world. But peel back the illusion, and everything you thought was firm becomes fog. Atoms, the so-called building blocks of reality, are almost entirely empty. If the nucleus of an atom were the size of a golf ball, the nearest electron would orbit nearly a kilometer away. The rest, a void, a vast, echoing nothingness. And yet you sit and breathe, and trust the world not to dissolve. This is the deception of matter. The lie it whispers not with malice, but with familiarity. A lie we're born into and almost never question. Until now. Because when we ask, what is matter really made of, the answers dissolve faster than we can hold them. We find ourselves chasing ghosts through empty space, catching glimpses of reality through a quantum keyhole that always moves just out of reach. It is said that science begins with observation, that to touch is to know. But in the quantum world, touch is a trick. When you place your hand on a table, nothing, and I mean nothing, actually makes contact. Electrons in your skin repel the electrons in the table, both governed by an invisible force, electromagnetism. You feel resistance, yes, but no particles touch, no atoms collide. The feeling of solidity is an illusion projected by fields you cannot see. You have never truly touched anything in your life, and still, you believe in matter. But why? Perhaps because it obeys. It appears when you summon it. It supports your structures, it reflects your light, and yet, beneath the obedience is a wildness, a reality that refuses to be pinned down. Let's return to the atom, that ancient symbol of the indivisible. The Greeks named it atomos, meaning uncuttable. But they were wrong. We've cut the atom, again and again, and each time the pieces got stranger. First, we found protons and neutrons at the core, with electrons smeared in clouds around them. Later, even these were broken open to reveal smaller entities, quarks and gluons, governed by the strong nuclear force, but every layer peeled away only revealed more complexity, more uncertainty. The deeper we dig, the less the pieces behave like matter. Electrons, for instance, are not little balls orbiting like planets. They're probability clouds, regions where the electron might be, according to the strange mathematics of quantum mechanics. They don't travel in neat paths. They flicker. They exist in a state of superposition, being here and there and nowhere in particular until we try to look. Try to observe them directly and they collapse. The act of seeing changes the thing seen. In the world of matter, observation is participation, and reality behaves more like a question than an answer. This is not poetry, it's physics, and it upends everything. If electrons are not objects but statistical ghosts, if atoms are mostly emptiness, if contact is electromagnetic repulsion, then what is matter? Not a substance, not really, not in the way our senses pretend. Perhaps it is better described as structure without solidity, pattern without permanence, a scaffold of forces, not a collection of things. But even that is a guess, because physics, in its honesty, refuses to lie to us the way matter does. Physics admits what it doesn't know. And one of its most uncomfortable admissions is this: we do not know what matter is. We can measure it, we can manipulate it, we can even smash it into pieces inside billion-dollar machines. But ask what it is in the deepest sense, and the answers become slippery. Particles may be real, or they may be ripples, or statistical phenomena, or artifacts of deeper fields. The story of matter is no longer a tale of marbles in motion. It's a drama of vibrations in invisible fields, governed by math that doesn't yield pictures, only probabilities. And here, at this first cliff's edge, the deception becomes more than academic. It becomes existential. Because if matter is not solid, then neither are we. You are made of atoms, trillions of them, in bones and blood, in neurons and breath. But those atoms are mostly void. The particles within them, flickering, uncertain, entangled. At the smallest scale, your body is more like a wave than a wall, a song rather than a sculpture. So what are you, and what does it mean to be real in a universe where matter itself may not be? These are not abstract questions. They live in your skin. They echo in every footstep. They wait in the pause between thought and action, asking not only what you're made of, but whether being made of anything is even the right way to frame existence. And if the lie of matter is that it's solid, perhaps the truth is more beautiful. Maybe the real story is not about things, but about relations, not particles, but processes, not stuff, but structure. Maybe you've never touched anything, because touching was never the point. Maybe you were meant to feel not contact, but connection. And as we begin this descent, past atoms and fields, through quarks and clouds, into the wild and warping realm beneath solidity, ask yourself, if everything we touch is mostly empty, why does it still feel like something? We call them the building blocks of reality. Atoms, that ancient idea, resurrected by modern physics, still clings to its throne as the foundation of everything we know. Stone, steam, skin, starlight, all of it constructed from tiny, invisible bricks. But this architecture is deceptive, because atoms are not simple, and they are not solid. Their design is not built like a house, it's written like a riddle. Let's enter one now. An atom of hydrogen, the first, the lightest, the most abundant. At first glance, it seems simple. A lone proton at the center, a single electron somewhere nearby. Two components, one relationship, a microcosm of structure. But simplicity in physics is often a mirage. And even this, the most basic atom in the universe, harbors a storm of mystery. We begin at the center, the nucleus. The proton is not a solid ball. It is a seething storm of three quarks, bound together by gluons, force-carrying particles that behave more like tangled lightning than tidy mortar. The quarks themselves are never alone. No one has ever observed a free quark in the wild. Try to separate them, and the force between them strengthens, a phenomenon known as confinement. Pull too hard and you don't isolate a quark. You rip space enough to create a new quark-antiquark pair. Reality resists you with creation. This isn't architecture, it's alchemy. The proton is roughly a femtometer across, 1/4,000,000th of a meter. Yet it contains within it the blueprint for all chemistry, all biology, all structure. And it's not empty. It's dynamic. The quarks vibrate and jitter inside it, held in a constant dance by the strongest force in nature, the strong nuclear force. Move outward, and things get stranger still. The electron is often depicted as a tiny particle orbiting the nucleus like a planet around a star. That image is wrong, seductively wrong. Electrons do not orbit. They do not follow paths. They exist in orbitals, probability distributions where the electron might be found. Think of them not as marbles, but as smeared-out clouds of potential. In quantum terms, the electron exists as a wave function, a mathematical construct that tells us where it might be, but not where it is, until we look. And the moment we measure it, that wave function collapses. The electron chooses a location. But does it really? Or is it our act of measurement that gives it form? Some interpretations of quantum mechanics suggest the latter. That matter, or at least our experience of it, requires an observer, that particles do not possess definite properties until they are measured, that the very architecture of the atom and of everything built from atoms is not fixed, but conditional. We live inside that conditionality. Take the helium atom, for instance. 2 protons, 2 neutrons, 2 electrons. Already the orbital structures become more complex. The electrons repel each other, creating shifting zones of interference and balance. Each layer we add multiplies the complexity, not linearly, but exponentially. By the time we reach iron, the most stable nucleus known, We are dealing with dozens of particles interacting in ways that no classical metaphor can fully capture. These atoms are not billiard balls. They are solutions to equations coalesced into temporary stability. Atoms, it turns out, are processes, not objects. We treat them as objects because it suits us, because our world is built on sensations, and those sensations trick us into thinking of matter as stable. But atoms are more like verbs than nouns. They behave, they fluctuate, they respond. And here's something even more unnerving. No atom exists in perfect isolation. Every atom in your body is in subtle quantum dialogue with the world around it. Entanglements, field interactions, vibrations in the vacuum, all constantly shifting, never fully still. You are not built from bricks. You are woven from active, vibrating relationships. That weaving is held together, not by matter, but by forces. The strong force binds quarks into protons and neutrons. The electromagnetic force binds electrons to nuclei. The weak force allows particles to decay, transforming matter from one type to another. And gravity, well, gravity plays its long game at massive scales, holding atoms together only as part of the broader structure of stars, planets, and you. These forces don't simply act upon matter. They are the very reason matter has form. Strip them away and nothing holds. Atoms would disintegrate, nuclei would fly apart, electrons would escape. You would dissolve into unpatterned energy. It's almost poetic. What we call matter isn't matter at all. It's balance, tension, relationships. Even within a single atom, this balance is astonishing. The repulsion between electrons and the pull of the nucleus must be perfectly tuned. Slight variations and chemistry collapses. Life becomes impossible. The architecture falls, and yet it holds. It held in the early universe when atoms first formed in the cooling afterglow of the Big Bang. It held in the cores of stars, where atoms fused and gave birth to the elements of life. It held in the dust that coalesced into planets, and the cells that formed in oceans, and the thoughts that swirl now behind your eyes. Atoms, fickle, ghostly, improbable things, built all of it.
But do not mistake them for reliable.
They are not static. They tunnel, they decay, they entangle, they vanish and reappear with rules that seem written by riddles. Their architecture is not marble columns, it's interference patterns, probabilities, waves. We cannot even draw them accurately. The more precisely we define their position, the more we lose their momentum, and vice versa. This is not a limit of technology. It is a fundamental truth of the quantum world. It is called the Heisenberg uncertainty principle, and it says the more you try to pin an electron down, the more it slips through your grasp. Atoms do not allow you to know them completely, and perhaps that is their final secret. That what matter is made of is not a thing, but a mystery wrapped in laws. Laws that refuse to be touched, that allow just enough coherence for life to emerge, but never quite enough certainty to make sense of it all. As we prepare to dive deeper into the nucleus, into the quarks, into the forces behind them, remember this: matter may be what builds the world, but mystery is what holds it together. The closer you get to the heart of matter, the less it behaves like anything that should exist. We now leave behind the drifting probability clouds of electrons and dive into the core, the nucleus, where protons and neutrons gather in tight, furious communion. This is no gentle place. It is a storm held together by sheer force of nature, by a power so immense, so unrelenting, that it has no rival in the known universe. Welcome to the domain of the strong nuclear force, the force that keeps the heart of atoms from tearing themselves apart. Let's start with a paradox. Protons are all positively charged. According to electromagnetism, like charges repel. So, in the center of every atom, these protons should be blasting away from each other, exploding the nucleus from within. And yet, they don't. They remain bound, clustered tightly with neutrons in the nucleus, defying that repulsion. Why? Because of the strong force. the most powerful of the four fundamental forces of nature. Unlike gravity, which pulls everything gently toward everything else, or electromagnetism, which governs attraction and repulsion at a distance, the strong force is peculiar. It only acts at extremely short ranges, about a femtometer, or 1/4,000,000th of a meter, and within that range it overwhelms all else. But the strong force doesn't work like glue. It's not a static bond. It's more like a storm of tension, constantly negotiating with itself. It's mediated by particles called gluons, named with a touch of poetic simplicity for their role as the glue of the nucleus. But gluons don't simply pass messages between protons and neutrons. They trap them, they confine them, they form an energetic prison from which nothing escapes. Zoom in further, and you'll see why. Protons and neutrons are not solid particles. They're made of quarks, fundamental particles that come in types whimsically labeled up and down. A proton contains 2 up quarks and 1 down, a neutron 2 down and 1 up. These quarks are held together inside their host particle by gluons, which constantly whip between them like bolts of raw force. But try to separate a quark from its companions, and the force doesn't weaken like a stretched spring. It intensifies. It's like trying to pull apart a rubber band that gets stronger the more you pull. If you yank too hard, something bizarre happens. The energy you've input into pulling doesn't tear the quark free. Instead, it creates a new quark-antiquark pair from the vacuum. You never get isolation, you get duplication. This phenomenon is known as color confinement, though the term color has nothing to do with hue and everything to do with a bizarre quantum property of quarks. It's a kind of bookkeeping, a way to ensure the math works out. But the principle is real. Quarks cannot exist alone. They are forever bound in groups, trios for protons and neutrons, pairs for mesons. They are social at a level deeper than logic. They are woven into the structure of reality, always part of something larger. This binding isn't optional. It's not cooperative, it's enforced. The nucleus is not a friendly gathering of particles. It's a cold, beautiful prison, locked tight by rules written into the universe itself. And yet, the balance must be perfect. If the strong force were just a bit weaker, atomic nuclei wouldn't hold together. If it was stronger, nuclear fusion in stars would stall. In either case, the universe as we know it would not exist. Chemistry, biology, thought, all dependent on a razor-thin slice of force calibration. Even neutrons and protons owe their identities to this balance. A free neutron, left outside the nucleus, is unstable. It decays in about 10 minutes into a proton, an electron, and a ghostly neutrino. But locked inside a nucleus, the neutron finds equilibrium. It becomes essential. It adds mass, it moderates repulsion, it stabilizes the atom's heart. But that stability is not permanent. In heavy elements, like uranium, the nuclei swell with too many protons. The strong force begins to lose its grip against the repulsive scream of all those positive charges, and eventually it breaks. The nucleus splits, fission, a chain reaction, and with it, the strongest force becomes the most dangerous, harnessed by stars, by reactors, by bombs. There is an exquisite irony here. The very force that holds matter together is also the one that can tear it apart. But there's more lurking in this nuclear sea than just protons and neutrons. Deep inside, the strong force doesn't operate alone. It mingles with the weak nuclear force, responsible for particle decay and transmutation. This quiet, ghostly partner allows for the alchemy of the universe, for protons to become neutrons, and vice versa, enabling the nuclear reactions that forge the elements in the bellies of stars. And still, we do not fully understand this realm. We can calculate its effects, we can simulate the interactions, but what actually is a gluon? Why do quarks come in threes? Why do they never roam free? We've built particle accelerators the size of cities just to glimpse their behavior. We've collided protons at near light speed and recorded the aftermath like archaeologists of the invisible. And still, the nucleus holds secrets. At these scales, space itself begins to quiver. Quantum fluctuations, random ephemeral shifts in energy, become impossible to ignore. The very vacuum within and around the nucleus seethes with activity. Particles blink into and out of existence. Forces ripple across emptiness. The nucleus is not a structure. It is a symphony played on an instrument made of uncertainty. So next time someone points to a model of an atom, neat spheres stacked like marbles, smile politely. Then remember, what's really inside the nucleus is not a tidy set of balls. It's a seething quantum furnace, a prison of fundamental particles, a dance of confined quarks and unleashed energies, and the very blueprint for how reality holds itself together. Until it doesn't. Because if matter is what makes us, the nucleus is what binds us. And once we understand its rules, we might finally glimpse what lies beyond them. Venture past the edge of the nucleus, and you find yourself not in clarity, but in chaos. You are no longer in the realm of atoms or even protons and neutrons. You have passed into a deeper stratum, one that mocks our metaphors and fractures our understanding. Welcome to the quark frontier. We once believed protons and neutrons were indivisible, the true atoms in the Greek sense, atomos, that which cannot be cut. But nature is rarely so accommodating. What we thought were particles turned out to be composites, bundles of even smaller, stranger constituents, quarks. Quarks are the true cryptic architects of matter, and they are nothing like what we imagine when we think of particles. There are 6 types, or flavors, of quarks: up, down, charm, strange, top and bottom. Names chosen not for clarity, but almost in defiance of it. At first, only 2 seemed relevant to ordinary matter: up and down. 2 ups and a down form a proton. 2 downs and an up form a neutron. Simple enough, on the surface. But the world of quarks is anything but simple. Quarks are never found alone, ever. No one has ever isolated a single quark. It's not that we haven't tried, we have, with billion-dollar machines and collisions at the edge of light speed, but the harder we try to pull a quark from its partners, the more space resists. The strong force intensifies, growing stronger with distance, an inversion of almost every other force we know. This resistance culminates in something utterly bizarre. As you pull quarks apart, you don't get isolation, you get creation. The energy required to separate them snaps reality itself, and a new quark-antiquark pair emerges from the vacuum. The prison of confinement never breaks, it just multiplies. This is color confinement, a quantum phenomenon with no classical analogy. And here, color doesn't refer to red or blue in the way we see them. It's a quantum property, like charge or spin, used to keep track of quark interactions. Quarks must combine in ways that neutralize this color, always in pairs or trios that sum to a colorless state. Nature demands it. It is a rule with no exception. But why? Why do quarks behave this way? Why are they so stubbornly communal? The answer may lie in the messengers between them, the gluons. These force carriers are the mediators of the strong interaction, ferrying the binding force between quarks. But unlike photons, which carry the electromagnetic force and do not interact with each other, gluons themselves carry color charge. This means they interact with other gluons, creating a tangled web of force, a self-interacting storm of bonds and feedback loops. Imagine trying to untangle a knot, only to discover that the rope ties itself tighter the more you pull. That is the territory we now inhabit. And yet, despite all this confinement, we can glimpse quarks indirectly. When protons are smashed together at enormous energies as they are in the Large Hadron Collider, the collision shatters them into fragments. What emerges from the wreckage are jets of particles, cascades of mesons and baryons, which betray the presence of quarks inside. It's like watching a bomb explode and reconstructing the bomb maker's tools from the debris. But even these reconstructions raise deeper questions. Because the strong force that binds quarks is responsible for something else entirely: mass. We often think of mass as something fundamental, that protons and neutrons have mass because their constituent quarks do. But here's the twist. The mass of a proton is far greater than the mass of its 3 quarks. In fact, over 95% of a proton's mass comes not from the quarks themselves, but from the energy of their interaction. This is not a metaphor. It's Einstein's famous equation in action, E equals mc squared. The energy of the strong force, the frenetic seething dance of quarks and gluons, becomes mass, becomes substance, becomes you. You are not made of matter, you are made of the tension between things that cannot be separated. This idea is as beautiful as it is unnerving. Mass is not some fundamental stuff, it is emergent. It arises from interaction, from process, from constraint. Matter at its deepest level is not a thing, it is a relationship. And yet, there are layers even deeper. The 6 quark flavors are part of what physicists call the Standard Model, a tidy but incomplete theory of fundamental particles and their interactions. Most of the matter we see is made from up and down quarks. The others, strange, charm, top and bottom, are heavier, rarer and unstable. They flicker briefly into existence in particle accelerators or cosmic ray collisions, then decay into more stable forms. But their very existence poses haunting questions. Why are there 6 types of quarks at all? Why these masses, these lifetimes, these decay patterns? Is there an unseen symmetry, a hidden reason? The top quark, for example, is the heaviest particle in the Standard Model, as massive as an entire gold atom. Yet it exists for less than a trillionth of a second. It's so heavy, so short-lived, that we don't even see it directly. We see echoes of its decay, its imprint. Why should such a colossal particle exist at all? Some theories suggest that quarks are not truly fundamental, that they are made of even smaller constituents. Others invoke supersymmetry, extra dimensions, or strings vibrating in multidimensional space, but none of these have been confirmed. For now, the quark remains the frontier, a riddle that mocks our metaphors, a building block made of uncertainty, a whisper that matter is not what we thought it was, and perhaps never was. In the next part, we will explore the world of fields, invisible, omnipresent, the true substrate beneath particles. Because to understand what matter is, we must also understand what it emerges from. Matter, after all, may not be built. It may be born, rippling out from the void as a fleeting resonance on the canvas of something far stranger. If you strip away everything, the atoms, the nuclei, the quarks, what remains? Not emptiness, not silence, not nothing. What remains is the field, invisible, all-pervasive, eternal. In the deepest models of physics, fields are the true foundation of reality. They are not secondary to particles, they are the origin. And the particles we've come to know, electrons, quarks, even photons, are not fundamental objects but vibrations in these fields. Matter is not made of things. It is made of excitations in an invisible medium that stretches across the cosmos. It's a concept that defies intuition. The idea that the entire universe is filled with invisible fields, each one representing a different particle species, sounds more mystical than physical. But this is no speculation. It is the cornerstone of quantum field theory, our most accurate, most battle-tested description of nature. There is an electron field, present everywhere. It exists in the void between galaxies, in the depths of interstellar space, in the space between atoms. It is always there. And what we call an electron is simply a localized ripple in that field. Likewise, there is a quark field, a photon field, a gluon field, even a Higgs field. Every particle we've ever observed is a note played on one of these invisible instruments, a quantized vibration rising briefly above the hum of the quantum vacuum. So when we ask, what is matter made of, we must reckon with a deeper truth. Matter is what happens when fields are disturbed. These aren't fields in the classical sense, like wind sweeping through grass. They are quantum in nature. That means they aren't smooth or continuous. They flicker, they jitter, they seethe with uncertainty. Even in the lowest possible energy state, the so-called vacuum, these fields are not calm. They are alive with zero-point energy. Particles appear and disappear. Virtual quanta interact and vanish. What we call empty space is not empty at all. It is a boiling sea of fields, pregnant with possibility. This is perhaps the greatest betrayal of the classical worldview. That space is not a stage. It is an actor, a participant. The void is not passive. It is the very source of particles, a canvas on which matter is painted, but also the brush that paints it. Take the Higgs field, for example. Unlike most fields, the Higgs field has a non-zero value everywhere, even in its vacuum state. It permeates all of space like a fog. And as particles move through it, they interact with this field. The more strongly they interact, the more mass they acquire. In this way, the Higgs field acts as a kind of drag, a resistance against motion, but not against all particles equally. Some glide through it almost untouched, like photons. Others, like the top quark, struggle as if wading through cosmic syrup. The degree of interaction with this field determines how much inertia, how much being a particle possesses. Mass, in other words, is not intrinsic, and it is bestowed by the field. It's a staggering idea. The reason you have weight, the reason stars collapse, the reason black holes form, all of it traces back to this invisible field that grants mass to otherwise weightless entities. It is not gravity that gives things heft. It is the Higgs. And yet, we only confirmed the Higgs boson, the quantum excitation of this field, in 2012. For decades, the Higgs was a theoretical ghost, a missing puzzle piece in the Standard Model. Its discovery at CERN's Large Hadron Collider wasn't just a triumph of science. It was a moment of cosmic revelation, a brief, glorious confirmation that beneath matter is a silent field shaping everything. But if every particle is just a ripple, a vibration, a localized blip in a field, what then are we? Is the self just a standing wave, a transient pattern of energy confined in a lattice of space? If so, permanence is an illusion. Solidity is a trick of scale. What we call a person or a planet or a proton is not a thing but a dance, a sustained choreography of quantum fields. Even stranger is what happens when these fields overlap and interfere. Particles can arise from multiple field interactions. Forces are transmitted by exchange particles, which are themselves field excitations. In this model, everything, from light to time to entropy, is a consequence of field interactions. It's not merely that fields cause particles, it's that only the fields are real. And reality then is less like a machine and more like a symphony. Yet this symphony is not deterministic, it's probabilistic, governed by quantum uncertainty. The fields don't evolve smoothly. They evolve by rules that allow for possibilities, not certainties. At every point in space, every second of time, reality rolls the dice. And we, our bodies, our thoughts, our very atoms, are the winners of an unimaginably vast quantum lottery. Some physicists believe that beyond these fields, there might be a single unifying field, a deeper foundation from which all others arise. This would be the dream of a theory of everything. String theory, loop quantum gravity, and other contenders aim to describe it, but none have succeeded, not yet. Until then, the field remains a mystery, both solved and unsolved. We can describe it, we can manipulate it, but we do not truly understand why it behaves as it does. We know only that it is there, beneath everything, writing the story of matter in a language we're just beginning to hear. And in the next chapter of this story, we'll look beyond the fields themselves to the forces they generate, because if matter is born of fields, it is shaped, sculpted by the four fundamental interactions that govern our universe. And in that forge, matter does not merely exist, it evolves. So now we know, Matter is not built from bricks, but born from tremors, from fields that stretch across the cosmos and ripple into form. But if fields give rise to particles, what governs what happens next? Why do atoms form? Why do stars burn? Why doesn't the universe dissolve into chaos? The answer lies in four invisible architects, four interactions that shape the behavior of everything, from the tiniest quantum spark to the bones in your hands. They are not forces in the way we usually think of them, as pushes and pulls. In quantum field theory, these forces are more like rules of engagement, enforced by the exchange of force carriers, bosons, between particles. These are not metaphors. These are transactions, real exchanges that determine what sticks, what falls apart, and what becomes real. Let's begin with the most familiar, gravity. Despite being the weakest force by far, gravity dominates our visible universe. Why? Because it never cancels out. Every atom attracts every other atom. There's no anti-gravity charge to oppose it. It is relentless, accumulative, infinite in range. It is the sculptor of galaxies, the architect of solar systems, the quiet hand that turns dust into stars and stars into black holes. And yet, gravity remains the least understood of the four forces. In the Standard Model, gravity doesn't fit. It lacks a quantum description. There is no confirmed graviton, no force-carrying boson. General relativity treats gravity as the curvature of space-time itself, not as a field. This leaves a fracture in our understanding, a rift between the quantum and the cosmic. But we move on to the electromagnetic force, a force of elegance and reach. Electromagnetism is mediated by photons, massless particles that carry light, yes, but also bind electrons to nuclei and determine the structure of atoms. It is the reason matter has form. It's why molecules assemble, why chemistry works, why you can see, why a magnet clings to a fridge, every spark of lightning, every thought in your brain, all electromagnetic transactions. And unlike gravity, this force can cancel. Positive and negative charges attract and neutralize, allowing for complex balances. Its range is infinite, but its effects fall off with distance, unlike gravity, which gathers mass to become stronger. This makes electromagnetism the master of the intermediate scale, where matter takes on complexity without collapsing. Now deeper, stranger, the strong nuclear force, the glue that binds quarks into protons and neutrons, and those into nuclei. It is the strongest of all forces, but its influence is tragically short-ranged, effective only at distances smaller than a femtometer. Beyond that, it drops off like a cliff. This is the force of confinement, of binding, of resistance. Without it, the positively charged protons in your nucleus would repel each other with such violence that atoms and life would be impossible. It holds them together with astonishing strength, mediated by gluons, which interact with one another in tangled webs of color charge. It is not a gentle force, it is violent, saturated, raw, and yet from it comes stability, the bedrock of all visible matter. And then there is the weak nuclear force, the most elusive and the most misunderstood. It is not weak in power, but in reach. It governs decay, transformation. It is the force behind radioactivity, behind the alchemy that turns one element into another. It enables beta decay, in which a neutron transforms into a proton, emitting an electron and a ghostly neutrino. Without the weak force, the sun would not shine. Fusion could not proceed. Heavy elements would never be born in stellar cores or supernovae. It is the force of change, of mutation, the great transmuter. And so we have them, the four fundamental forces: gravity, shaping the cosmos; electromagnetism, shaping the atom; the strong force, binding the nucleus; the weak force, driving transformation. But why only four? Why these four? Why not 5 or 17? No one knows. We've searched for unification, a grand unified theory that would tie them all together, show them as facets of a single primal force, and we've come close. At high energies, the electromagnetic and weak forces unite into the electroweak force. The Standard Model describes this successfully, but gravity refuses to join the family, and so the dream of unification remains. Just that. A dream. Or perhaps a destiny still out of reach. What's more, these forces may not be constant. In certain cosmological models, their strengths can vary over time or across regions of space. If true, this would have profound implications. Matter may be more fragile, more contingent than we've ever imagined. And here's a deeper twist. These forces don't just shape matter. They determine what kinds of matter can exist at all. Change the strength of the strong force slightly, and protons don't form. Change the strength of gravity, and stars burn too fast or never ignite. Alter electromagnetism, and atoms fall apart. Our entire reality sits on a knife's edge, a delicate balance of four invisible rules. No tinkering allowed, no room for error. This is not engineering, this is tuning at the level of cosmic law. A fine-tuned orchestra with no known conductor, unless there are other realities where the notes are different, where the forces play a different song. In those universes, perhaps matter never coheres. Perhaps it sings in keys we cannot hear. Or perhaps, in some deep, multiversal silence, the forces we know are merely one arrangement among an infinite library of possible realities. But in our universe, these four forces reign. They shape the stage on which matter performs its great play. They bind the cast, they direct the motion, they limit the improvisation. And so, matter is not free, it is governed, defined not just by what it is, but by what it must obey. And in the next part of our journey, we'll turn to the architecture of matter, how the rules and building blocks combine into atoms, molecules, and the structured complexity that gives rise to everything from granite to galaxies. Because matter, while bound by law, is not simple, it is organized. Now that we've uncovered the silent forces shaping matter's behavior, we descend one layer closer to something deceptively familiar: structure, atoms, molecules, solids, liquids, gases, the tangible world. But what may feel stable, permanent, even inert, is anything but. Matter, even in its most static forms, is the result of a dynamic architecture, one forged by field interactions, fundamental particles, and a symphony of probabilities. Let's begin with the atom, a name derived from the Greek word atomos, meaning indivisible. The irony, of course, is that atoms are not indivisible at all. They are elaborate assemblies, architectural miracles of nature that defy sheer chaos through subtle balances. At the heart of the atom lies the nucleus, a dense knot of protons and neutrons. It occupies just 1/10,000th of the atom's total diameter, and yet contains nearly all of its mass. Protons carry a positive electric charge. Neutrons, as their name suggests, are neutral. Both are made of quarks, bound tightly by the strong nuclear force. That force is so intense it keeps the positively charged protons from flying apart, a testament to nature's ability to wage an invisible war for the sake of order. Around this dense center dances a cloud, the electron cloud. Electrons, the lightest charged particles in the Standard Model, don't orbit the nucleus like miniature planets. That model died with classical physics. Instead, electrons exist as probability clouds, quantum blurs, where we can only estimate the likelihood of finding one at any given location. They form orbitals, not orbits, shapes defined not by gravity, but by solutions to Schrödinger's equation. Some orbitals are spherical, others are dumbbell-shaped, others still defy visualization. Each represents a standing wave, a resonance condition set by the constraints of charge, energy, and quantum spin. What emerges from this chaos of uncertainty is something startlingly organized: the periodic table of elements. Each element is defined by the number of protons in its nucleus, its atomic number. Change that and you change the very identity of the atom. Add a proton to hydrogen and you get helium. add another, lithium. And on it goes, 118 known elements, each with a distinct electron configuration and therefore distinct chemical properties. Yet the proton is not some Lego brick you can just snap into place. It must be balanced by electrons, else the atom becomes an ion. It must exist within a stable nuclear configuration, else it becomes radioactive. Adding protons becomes harder and harder, and past a certain point, even the strongest force in nature can't hold the nucleus together. At that edge lies instability and decay. But when atoms do stabilize, when their electrons find harmonic configurations in discrete energy levels, they become capable of something astonishing: bonding. This is the beginning of chemistry, of molecules, of the vast combinatorial architecture of the physical world. Electrons can be shared between atoms, covalent bonding, donated and received, ionic bonding, or held in weaker, more transient relationships, van der Waals forces, hydrogen bonds. These bonds arise from the same electromagnetic force we discussed earlier, yet give rise to wildly complex outcomes: water, proteins, crystals, DNA. Matter, once merely the child of quantum fields, now becomes language. With bonding as syntax and atoms as letters, molecules become sentences. Some simple, some so complex they encode the instructions to build life itself. And still, it scales. Molecules assemble into structures, lattices, membranes, polymers. The geometry of these assemblies, their angles, lengths, and symmetries, determines their macroscopic behavior. Carbon, for example, can arrange itself as graphite, soft, flaky sheets that slide past one another, or it can form diamond, the hardest natural material known, a tetrahedral fortress of atomic precision. Same element, different structure, radically different properties. This is the hidden dimension of matter. Structure defines function. At higher levels still, matter becomes phase-bound, solid, liquid, gas, plasma, each phase governed by temperature, pressure, and molecular mobility. Solids resist deformation, liquids flow, gases expand. Plasmas, the fourth and most exotic common state, consist of charged particles torn from their atomic prisons, free to move and respond to electromagnetic fields. And then there are exotic phases: Bose-Einstein condensates, superfluids, time crystals. These rare configurations challenge our understanding of matter itself, demonstrating that under extreme conditions, particles can synchronize, flow without resistance, or oscillate across time. This architecture, intricate as it is not merely physical, it is hierarchical. Particles form atoms, atoms form molecules. Molecules form structures, structures form objects, objects form systems, systems form galaxies. And somewhere, deep within that layering of form upon form, you emerge. The brain you're using to listen, made of cells, made of molecules, made of atoms, made of particles, is itself the product of matter's architecture. And within that brain lies something even stranger, the emergent phenomenon we call mind. But we are getting ahead of ourselves. For now, let us pause on the threshold of the everyday world, a world made tangible by forces we cannot feel, arranged by probabilities we cannot see. Because all that complexity, all that form, still rests on one assumption: that the matter we observe is all there is. And yet, it isn't. Because most of the universe's mass doesn't come from atoms, or protons, or anything we can touch. It comes from something else, something darker, something missing. We've spoken of atoms, of particles, of forces and architecture, of all the visible scaffolding that builds the world we know. But now, we arrive at a riddle that tears through the heart of everything we've established, the riddle of missing mass. In the early 20th century, astronomers assumed what seemed obvious: the stars in a galaxy orbit due to the gravitational pull of the other stars around them. Newton's laws, Einstein's refinements, elegant and predictable. The farther a star was from the galactic center, the slower it should spin.
But when Vera Rubin meticulously charted the rotation curves of galaxies in the 1970s, something shocking emerged. The outer stars weren't slowing down. They were spinning at the same speed as the inner ones, far too fast for the visible mass to be holding them in orbit.
According to the laws of gravity, those stars should be flung into the abyss. But they weren't. Something invisible, was anchoring them, wrapping galaxies in a gravitational grip stronger than their luminous matter could ever explain. That something became known as dark matter. We named it not because it is dark in color, but because it is undetectable by light. It neither emits nor absorbs electromagnetic radiation. It does not shine. It does not reflect. It is invisible, not just to our eyes, but to every photon in the universe. And yet, it makes up the majority of matter in the cosmos. Estimates suggest that all the stars, planets, dust clouds, and galaxies, everything that emits light, accounts for less than 5% of the universe's total mass energy content. Roughly 27% is dark matter, and the rest, about 68%, is something even stranger, dark energy. We'll return to that later. For now, the missing mass. We have never seen a particle of dark matter, but we see its fingerprints everywhere, in the structure of galaxies, in the way galaxy clusters bend light from behind them, a phenomenon known as gravitational lensing, in the ripples of the cosmic microwave background, the afterglow of the Big Bang. It's there, shaping the cosmos like a silent sculptor behind a veil. But what is it?
This is where the mystery deepens, and where the confidence of physics begins to tremble.
For decades, theorists proposed a class of particles called WIMPs, weakly interacting massive particles. They would interact through gravity and the weak nuclear force, but not electromagnetism. They could pass through a planet like wind through a ghost, and yet be massive enough to warp the orbits of stars. Experiments were launched deep underground, in abandoned mines shielded from cosmic radiation, hoping to catch just one WIMP in the act of passing through a detector. Decades passed. Nothing. Then came axions, hypothetical particles that could explain both dark matter and other puzzles in quantum chromodynamics. Other theories suggested sterile neutrinos, supersymmetric particles, or even primordial black holes. All elegant, all unproven. The failure to detect any candidate particle has led some physicists to question whether dark matter is even matter at all. Perhaps our understanding of gravity is flawed. Perhaps on cosmological scales, the force does not behave as we expect. This led to theories like modified Newtonian dynamics, MOND, or tensor vector scalar gravity, TVES. But these too failed to fully explain the data. The Bullet cluster, two colliding galaxy clusters, revealed a separation between visible matter and gravitational influence that modified gravity theories struggle to reconcile, so we remain in the dark, literally. What we do know is that dark matter does not clump the way normal matter does. It does not form atoms. It does not interact with light. It does not seem to participate in chemistry, thermodynamics, or radiation. But it does influence structure on cosmic scales. Without it, galaxies wouldn't form. The cosmic web, that great lattice of filaments and voids connecting clusters of galaxies, wouldn't exist. The universe would be featureless, smooth, empty. Dark matter is the invisible skeleton of the cosmos, and perhaps even more unsettling. It may be all around us, streaming through your body, through the walls, through the earth. As much as 100,000 dark matter particles may pass through you every second, undetected, unnoticed, but profoundly real. It is not the dark we fear in the woods. It is a different kind of darkness, perfectly indifferent to us, and yet essential to our being. And here's the philosophical rupture. We often think of matter as what's real, what we can touch, what we can see. But if 85% of the universe's matter is untouchable and invisible, what does that say about our definition of reality? Is the universe we perceive merely a shadow of the true structure?
a byproduct of something deeper, something hidden? What if, in some unknowable way, the matter we know is the anomaly, and dark matter is the rule? This flips our perspective, inverts the narrative. We are not built from the stuff of the cosmos. We are built from its exception. We exist within the gravitational confines of something vast, unknowable, and unseen. And just like antimatter, dark matter may hold a kind of mirror to the world we know. There may be dark atoms, dark forces, entire dark galaxies drifting through the void, unaware of us as we are of them. A shadow cosmos just beyond reach. Is this science fiction? Perhaps. But every major breakthrough in science, every quantum leap, began as a question too strange to ask aloud. And so we ask it, we search, and in the next part of our journey, we'll explore the most elusive building block of all, the neutrino, a ghost particle so vanishingly light, so inert to the world, that it may hold the key to both matter and its missing counterpart. Because if the visible world is just a fraction of the truth, what else have we missed? They are called ghost particles, not because they haunt, but because they pass through our world as if it were smoke. Every second, trillions of them stream through your body, through the walls, through the earth itself, without leaving a trace. You have never seen one, you have never touched one, but they are there, always. Ancient, indifferent, and perhaps essential. They are neutrinos. First predicted in 1930 by Wolfgang Pauli, almost reluctantly, as a desperate fix to a broken equation, neutrinos were meant to be the invisible glue that preserved the law of conservation of energy during radioactive beta decay. Pauli wasn't thrilled by the idea. In his own words, "I have done a terrible thing. I have postulated a particle that cannot be detected." And for decades he was right. It wasn't until 1956 that neutrinos were finally observed, not directly but through their effects, deep inside a nuclear reactor experiment conducted by Clyde Cowan and Frederick Rains. It was like trying to detect wind by watching a single blade of grass bend, but it worked. The neutrino, once a ghost in the math, became real. But what kind of real? That's where the strangeness begins. Neutrinos are elementary particles, members of the lepton family, like electrons. But unlike electrons, they carry no electric charge, making them immune to the electromagnetic force. They are incredibly light, so light, in fact, that for decades we thought they were massless. And most of all, they hardly ever interact with anything. You could shoot a beam of neutrinos through a wall of lead a light-year thick, and most would pass through untouched. They are, in every sense, the silent observers of the cosmos. And yet, their silence hides secrets. Neutrinos come in 3 known flavors: electron, muon, and tau. And bizarrely, they don't stay in their lane. As they travel through space, they can oscillate, morphing from one type to another. This quantum shape-shifting implies a profound truth. Neutrinos must have mass. This single fact shook the foundations of the Standard Model. The model, that intricate tapestry of known particles and forces, had no place for massive neutrinos. Their mass meant the model was incomplete. And if something so fundamental had slipped through the cracks, what else had we missed? The implications are staggering. Some physicists believe that neutrinos may hold the answer to one of the universe's greatest mysteries: why there's more matter than antimatter. In theory, the Big Bang should have produced equal amounts of both. They should have annihilated each other completely. And yet, here we are. 1 in a billion particles survived. Why? Neutrinos may be the key. There exists a hypothesis, elegant if unproven, called leptogenesis. It suggests that in the earliest moments of the universe, neutrinos, or their theoretical heavier cousins, may have decayed in a way that violated the expected symmetry between matter and antimatter. In other words, neutrinos may have tipped the cosmic scales, allowing matter to survive while antimatter vanished into history. Even more tantalizing, some physicists believe neutrinos may be their own antiparticles, a concept known as Majorana particles. If true, it would blur the line between matter and antimatter even further. A particle that is both itself and its mirror. That annihilates itself. That walks a razor's edge between existence and oblivion. If we could confirm this, if we could detect a process called neutrinoless double beta decay, it would rewrite our understanding of identity in the particle world, and with it, perhaps unlock the very mechanism by which the universe became more than nothing. But there's more. Neutrinos are not just theoretical players, they are cosmic messengers. During a supernova, the death throes of a massive star, 99% of the energy is released not as light or heat, but as a blinding burst of neutrinos. These neutrinos race ahead of the blast, carrying news of the star's death across space. In 1987, such a burst was detected on Earth from a supernova 168,000 light-years away. It arrived hours before the light did. In that moment, neutrinos proved themselves not just particles, but harbingers, a silent advance guard from the most violent events in the cosmos. And yet they are still largely unknowable. We build massive underground detectors in mountains, in abandoned mines, filled with ultra-pure water or exotic liquids, hoping that just one neutrino will interact. And when it does, it leaves only the faintest whisper of its passing. A flash of light, a barely measurable trace. We have captured only a sliver of their story, but we know this: neutrinos are everywhere. They were forged in the first seconds after the Big Bang. They stream endlessly from the sun, from exploding stars, from black hole collisions. They are a cosmic background hum, older than any light, harder to silence than gravity itself. And they may be billions of times more numerous than all the atoms in the universe. So we must ask, if such particles, weightless, chargeless, invisible, are so abundant, so foundational, are they the scaffolding of something deeper? Are we once again mistaking absence for irrelevance? In the silence of the neutrino, we may be hearing the hidden grammar of reality, the subtle mechanics that allow matter to exist, survive, and evolve. And perhaps, in understanding neutrinos, we are not just peeling back another layer of matter. We are peering into the soul of the machine itself. But one final leap remains, because the journey into matter's true nature cannot be completed by looking backward. It must look forward, to the theory that tries to unite it all. In the next chapter, we'll confront the grand attempt to bind all matter, all particles, all forces into one unbreakable equation, a theory of everything, and in doing so, we may discover what matter really is, or what it was always pretending to be. Throughout history, the greatest minds have been drawn to a singular obsession, the unification of all things. To find a single, elegant truth that binds the vastness of the cosmos to the smallest particle. A theory that doesn't just explain the universe, but completes it. This is the dream of a theory of everything. At first glance, it seems almost arrogant. How could one equation, one framework, possibly account for all the wild diversity of matter, from the turbulence inside an atom to the shape of the universe itself? But history gives us reason to believe. Newton unified the heavens and the earth. With gravity, he showed that the apple falling from a tree and the moon's orbit followed the same law. Maxwell later unified electricity and magnetism into electromagnetism, revealing light itself as a ripple in that invisible field. Then came Einstein. With general relativity, he replaced Newton's absolute space with a dynamic, curving space-time, a fabric bent by mass and energy. Gravity became geometry, time became elastic, and the cosmos was never the same. Each step was a revelation, but each left something behind. Relativity governs the large, but it crumbles in the quantum world, where uncertainty reigns and particles flicker in and out of existence like whispers in a storm. Conversely, quantum mechanics explains the small, yet fails to reconcile with gravity, that sovereign force of stars and galaxies. It's as if the universe speaks two languages, one of curves and one of probabilities, and we've yet to find the common tongue. This is the problem, and the prize. A true theory of everything would unite these realms, quantum and cosmic, particle and planet, into one coherent structure. It would explain all matter, all forces, all existence. The current leading framework, the Standard Model, is astonishing in its accuracy. It predicts the behavior of known particles and forces with exquisite precision. It gave us the Higgs boson. It powers our particle accelerators, our electronics, even the GPS signals that guide our daily lives. And yet, it is incomplete. The Standard Model ignores gravity. It has no explanation for dark matter, no accounting for dark energy. It requires dozens of parameters, masses, charges, couplings, that must be input by hand, without any deeper reason. It works, but it doesn't understand, and so the search for unification continues. Enter Grand Unified Theories, or GUTs. These propose that at incredibly high energies, far beyond anything we can currently achieve, the strong, weak, and electromagnetic forces merge into a single force, like three rivers joining upstream. Matter, too, would be unified, quarks and leptons seen as different faces of a deeper particle. Some guts predict the proton is unstable, capable of decaying over cosmic timescales. Others suggest monopoles, isolated north or south magnetic charges, should exist, relics from a hotter, denser past. We've never seen them, but then we're looking with flashlights into the depths of an ocean. Beyond the guts lies an even bolder attempt: string theory. Here, particles are not point-like, but tiny vibrating strings of energy. Each vibration mode corresponds to a different particle, an electron, a quark, a photon, all just variations of the same fundamental thread. String theory requires extra dimensions, perhaps 10 or 11, curled up and hidden from view. In its more advanced forms, it suggests entire branes, multi-dimensional surfaces on which our universe may be just one ripple. It is vast, mathematical, beautiful, but as of now untested. Critics argue that it predicts too much, that without experimental evidence it's not physics, but philosophy dressed as math. Supporters argue that it may be the only game in town, the only consistent way to combine quantum mechanics with gravity. And at the heart of that union is a particle that has yet to be found: the graviton. This hypothetical quantum of gravity, a massless spin-2 particle, would carry the gravitational force just as photons carry light. But no one has ever detected one, and perhaps we never will. Gravity is so weak at quantum scales that its particles may forever elude direct observation. Still, the pursuit continues. Because unification isn't just about technical elegance, it speaks to something older, deeper, almost spiritual. The yearning to believe that beneath all chaos there is order, that the universe is not a patchwork but a poem. But even this dream carries risk. The closer we look, the more we realize the theory of everything might not mean what we hope. It might not answer why there is something rather than nothing. It might not explain why these laws, not others. Why these particles, why these constants, why us? It may be in the end just a map of how, not a revelation of why. And yet, would that not still be sacred? To look upon the architecture of reality, to see for the first time the frame behind the veil? Or perhaps we are not meant to find it. Perhaps nature is not a single melody, but a chorus of overlapping themes, quantum, gravitational, dark, unknowable, forever out of tune with each other, and yet still forming a kind of harmony. Still, the pursuit matters, for in seeking to unify all matter, we are forced to confront the most humbling truth of all, that we too are part of the equation. Our minds, these fragile sparks of consciousness, are the byproducts of particles and forces dancing in an ancient pattern we barely understand. To explain the universe is to explain ourselves. In the next chapter, we descend once more, this time not into particles or theories, but into the very fabric beneath matter. Because if particles are vibrations, what is vibrating? What is space made of? The answer may not be matter at all, but something stranger. Something that reshapes everything we think we know about what's truly real. Imagine stripping the universe of every star, every atom, every speck of dust. Empty space, nothingness, silence. And yet, even in that perfect vacuum, something remains. It moves, it fluctuates, it trembles with unseen energy. Welcome to the world of quantum fields. For over a century, physicists have probed deeper and deeper into matter, splitting atoms into nuclei, nuclei into protons and neutrons, those into quarks. But the truth is, even quarks are not the end of the story. In modern physics, particles are no longer seen as tiny billiard balls or indivisible dots. They are excitations, temporary localized ripples in vast invisible fields that stretch across all of space. Every type of particle is tied to its own field. There is an electron field, a quark field, a photon field. And they are all layered over one another, overlapping, interacting, shaping the very nature of reality. In this view, what we call matter is just the momentary dance of fields catching energy. Let's take an electron. In the old view, it's a fundamental particle, a point with a negative charge. But in quantum field theory, what we see as an electron is really a blip in the electron field, a quantum of energy briefly gathered in one place. The electron doesn't move through space like a marble. Instead, the field vibrates in different places, and the vibration appears to migrate. It's not matter moving through space, it's space itself coming alive. And here's the mind-bending part. The vacuum, the place with nothing, is not empty at all. Thanks to Heisenberg's uncertainty principle, fields in a vacuum must constantly fluctuate. Even in the coldest, quietest corner of the cosmos, particles and antiparticles pop in and out of existence, borrowing energy from the vacuum and then vanishing before they're noticed. These are virtual particles, fleeting, unmeasurable, but real in their effects. Their presence shifts energy levels, alters atomic behavior. In one case, and the famous Lamb shift, their influence was measured so precisely it confirmed that even the vacuum is pregnant with possibility. But the most eerie demonstration of this is the Casimir effect. Place two uncharged metal plates very close together, a few nanometers apart, in a vacuum. Classical physics says nothing should happen. But quantum field theory predicts that fewer virtual particles can exist in the narrow gap than outside it, leading to a pressure difference. And so the plates move. They are pushed together by the vacuum itself. It's like watching nothing do something. This is the paradoxical heart of modern physics. The vacuum is not empty. It's a seething, turbulent sea of fields, invisible, omnipresent, and humming with energy. And this leads to one of the greatest mysteries in all of science. If the vacuum is filled with so much quantum energy, why doesn't it crush the universe? This is not a rhetorical question. According to quantum field theory, the vacuum should have an enormous energy density, enough to warp space, bend time, and accelerate the expansion of the universe to unimaginable speeds. Yet, the universe expands gently, calmly, with only a faint acceleration attributed to dark energy. The discrepancy between the predicted and observed vacuum energy is called the cosmological constant problem, and it is perhaps the most severe mismatch in all of physics, off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It's as if we expected the Earth to be the size of the observable universe and found it was actually a grain of sand. Something is wrong. Or missing. Some theorists believe this is where the final frontier lies, that within the quantum fields of the vacuum is a hidden code, a deeper reality that connects quantum physics with gravity, consciousness, and perhaps even time itself. And this brings us to the Higgs field, Among all the quantum fields, one is different, discovered, or rather confirmed when in 2012 at CERN, the Higgs field is responsible for giving mass to other particles. Without it, all particles would zip around at the speed of light, massless, chaotic, incapable of forming atoms, stars, or life. The Higgs field permeates all of space, everywhere, always. It is a background field, and as particles move through it, they interact with it, some more, some less, and that interaction gives them inertia or mass. Think of it like a kind of cosmic molasses. A photon glides through untouched, massless. A top quark plows through it and is dragged down, gaining mass. And when we collided protons with enough energy at the Large Hadron Collider, we excited the field enough to see its quantum ripple, the Higgs boson. It was not just a discovery, it was a confirmation that the vacuum shapes reality. The Higgs field is not some exotic extra. It's why matter holds together, why atoms exist, why there are elements, chemistry, planets, biology. The universe doesn't just exist in fields, it is fields. And we, our bones, our blood, our thoughts, are standing waves in this infinite, invisible ocean. But what stirs these fields? What determines how they behave? Why they exist at all? That remains a mystery. We don't yet know where fields come from, whether they are emergent, like patterns on water, or fundamental, like the water itself. Some physicists whisper about deeper structures, string theory, spin networks, causal sets that lie beneath the fields. Others suspect that information, not energy, not matter, may be the true foundation. But one thing is certain. When you look at matter, at a rock, a tree, your own hand, you are not looking at a solid thing. You are looking at a shimmering illusion held together by patterns in invisible fields, anchored by rules we barely understand. And yet, from these fields came galaxies and life and memory, from silence, music. In the next part of our journey, we explore one of the strangest consequences of these fields, one that challenges our very idea of thingness. A state of matter so bizarre it can defy gravity, flow forever, pass through walls. We leave the ordinary behind. Imagine cooling the universe down, slower, slower still, until even atoms begin to lose their individual identity, their motion quiets, their boundaries blur. And then, something remarkable happens. They merge. Not physically, but quantum mechanically. 100,000 atoms, behaving not like a crowd, but like a single entity. One wave, one function, one ghostly shape. This is the Bose-Einstein condensate, a state of matter so alien it might as well belong to another universe. First predicted in 1924 by Satyendra Nath Bose and Albert Einstein, it took almost 70 years before technology caught up. Only in the 1990s did physicists finally cool rubidium atoms to mere billionths of a degree above absolute zero, and witness the strange alchemy firsthand. At that temperature, atoms stop jostling and begin to overlap. Their wave functions, the quantum descriptions of their probability, stretch and expand until they are no longer distinct particles, but a coherent superfluid of matter. If that sounds abstract, think of it this way. Imagine a room full of violinists, each playing their own melody, chaotic and beautiful. As the temperature drops, they begin to tune to the same pitch, then the same rhythm. And finally, as the last heat dies away, they are no longer many. They are one instrument playing a note the universe has never heard before. This is what a Bose-Einstein condensate, BEC, is. Not just cold matter, but new matter. A single quantum wave stretched across macroscopic space, visible to the naked eye, behaving more like a field than like a collection of atoms. And it gets weirder. Specks can flow without friction. Spill them over a surface and they'll creep along indefinitely, unimpeded. They can climb walls, leak through barriers. They're not just super cold, they're super fluid. Even stranger, In this state, quantum effects, normally confined to the tiny world, suddenly become macroscopic. You can watch interference patterns. You can see matter diffract and bend as if it were light. You're not just studying quantum mechanics, you're watching it. But this state of matter is only one example of what lies beyond the classical world. There are others. Consider fermionic condensates, similar to BCs, but made from fermions like electrons instead of bosons like helium or rubidium atoms. These particles obey different rules. They can't occupy the same state, yet under extreme conditions they can pair up and mimic bosons, entering similar condensate states. It's through this process that superconductivity arises, the flow of electricity with zero resistance. Inside certain materials, cooled to specific critical temperatures, electrons form delicate pairs called Cooper pairs, slipping through the atomic lattice without scattering. Superconductors can levitate magnets, create lossless power lines, and hint at future quantum technologies that could rewrite computation itself. Then there's superfluid helium, not a theoretical construct, but a bizarre reality. Cool helium-4 below 2.17 Kelvin, and it undergoes a phase shift unlike anything in classical physics. It becomes frictionless. It can flow through cracks no molecule should fit through. In a container, it will crawl up the walls and out, as if it refuses to be contained. It's a liquid that defies gravity. And it's not alone. In the kaleidoscope of matter, researchers have discovered topological states, materials that conduct electricity on their surface but remain insulators inside. Their properties depend not on local chemistry but on global geometry, a feature more at home in abstract mathematics than atomic physics. These exotic materials, topological insulators, quantum spin liquids, time crystals, are just beginning to reveal themselves. And they are not just theoretical curiosities, they are being engineered. In labs around the world, physicists are creating conditions that nature never intended, pushing atoms into arrangements they've never known. The result is an emergent periodic table, not of elements, but of quantum phases. The old categories, solid, liquid, gas, plasma, are relics of a simpler age. We now live in a universe where entanglement, symmetry breaking, and collective quantum behavior define the frontiers of matter. And still, we are scratching the surface. Because each new phase discovered is not just a novelty, it's a window into the foundational architecture of reality. BCs show us that matter can lose its individuality. Superfluids show that resistance is not inevitable. Topological phases suggest that information, not substance, might define what something is. All of this leads to an unsettling realization. The further we push into the quantum frontier, the more alien matter becomes. And perhaps the most haunting idea of all. These strange states of matter, superfluids, superconductors, condensates, might not be confined to labs. They may exist in nature. Some theories suggest that neutron stars, the ultra-dense corpses of massive stars, may harbor superfluid interiors with matter flowing endlessly in locked, frictionless vortices. Others hint that the early universe, in its infancy, may have undergone phase transitions between different quantum vacua, shaping the very laws of physics we now take for granted. Which raises a final, unsettling question. Is the matter we see around us, solid, stable, familiar, really the default? Or is it just one branch of a deeper spectrum, a comfort zone in a sea of possible realities? We think of matter as fixed, reliable, but quantum mechanics tells us it is contextual, shaped by temperature, pressure, dimensionality, and even observation. In other words, matter is not what it is. Matter is what it does. And in the silence of a Bose-Einstein condensate, in that ghostly quantum hum where atoms become waves, we glimpse the truth. That even the most solid thing may be nothing more than a ripple in the void. In the next chapter, we descend further into this philosophical abyss, where identity, mass, and location begin to lose meaning. and the boundary between thing and nothing vanishes altogether. We ask the ultimate question: are particles even real? Particles. For over a century, we've imagined them as the fundamental bricks of matter, tiny dots with mass, charge, and location. Atoms once held that title until we split them. Then protons and neutrons took center stage until we cracked them open too. Quarks, leptons, bosons. The Standard Model now catalogues these so-called fundamentals. But something has always been off. We call them particles. Yet we've never truly seen one. No one has ever caught an electron sitting still or filmed a quark spinning in place. What we observe, through cloud chambers, through magnetic detectors, through the echoes of collisions, are trails, bursts, signatures, ghosts of something that once was, but the particle itself, always just out of reach. And then comes the riddle of duality. Sometimes particles behave like discrete points, like bullets zipping through space. But under different conditions, they diffract, interfere, spread like waves on a pond. The double-slit experiment, simple in setup yet profound in consequence, shattered classical intuition. Fire individual electrons, one at a time, at 2 slits. You'd expect 2 tidy clusters on the screen behind, but instead you get an interference pattern. Even when electrons are sent through alone, it's as if each electron passes through both slits simultaneously, interferes with itself, and chooses its landing at random. Not a particle, not a wave, something else. This is not a minor quirk, it's foundational and deeply unsettling, because it suggests that what we call a particle is not a thing, but a behavior, a kind of performance shaped by context. Ask a wave-like question, get a wave-like answer. Ask a particle-like question, get a particle-like result. It's as if reality is interpreting your inquiry and responding accordingly. So what is an electron, really? Is it a point mass, a probability cloud, a ripple in a quantum field? In the framework of quantum field theory, as we've explored, particles are localized excitations, ripples in invisible, omnipresent fields. But this too is a model, a language we use to speak about what we cannot touch. And it comes with limitations. For example, particles in quantum mechanics do not have defined positions and velocities. They have wave functions, mathematical objects that encode probabilities. An electron isn't here or there. It's a spectrum of maybes until an observation collapses the options into a single outcome. But even this notion of collapse is debated. Some interpretations, like the Copenhagen interpretation, suggest reality snaps into place upon measurement. Others, like many worlds, propose that every possibility plays out in parallel universes. That particles are simply the paths we perceive among countless branching timelines. And some physicists go even further. They suggest that particles may not exist at all, at least not in the way we imagine. They argue that what we observe as particles are merely epiphenomena, byproducts of deeper processes, that perhaps information, relations, or space-time events are more fundamental, and the idea of a self-contained, persistent thing is an illusion born from limited perception. Consider this: when we detect a photon, we don't see the photon traveling. We see a click, a moment of energy delivered. There's no journey, no trajectory, just an event, a cause, a result. Between source and detection, what happened? Was it a wave collapsing into a point? Was it a particle traveling through space? Or was it a kind of non-local handshake, a transaction across time, as some physicists suggest? In certain interpretations, like the transactional model, the future and the past co-author the present. Emission and absorption form a loop across time, and the particle is just the middle act of a temporal dance. Even more haunting are the delayed choice experiments. In these, we set up a situation where the decision to observe particle-like or wave-like behavior is made after the particle has already passed the slits, and yet the results seem to conform retroactively to the measurement we choose. It's as if the particle knew what you would ask before you asked it. If that doesn't unsettle the notion of a real independent particle, what would? Some physicists are now beginning to speak more about emergence than existence. The idea that particles are not pre-existing Lego bricks, but useful patterns that arise from deeper, unknowable rules. This isn't unprecedented. Temperature, for example, is not a thing. It's a statistical behavior, an emergent property of countless particles vibrating. In the same way, particles may be how reality organizes itself at our scale. A narrative we can follow, though the true machinery lies below. We see this hinted in high-energy physics. At extreme energies, particles begin to blur together. Their identities overlap, symmetries break. New behaviors emerge, behaviors that make no sense if you cling to the particle as a permanent object. It is also echoed in quantum gravity theories, where the very notion of space and time may dissolve at small scales. If space is emergent and a kind of hologram, then so too must be anything in it, including particles. And perhaps most tellingly, in quantum entanglement, we find particles that are linked across distance, their properties correlated in ways that defy classical logic. Measure one, and the other's state snaps into place, instantly, no signal, no travel, just connection. If particles were truly isolated entities, how could this be? Unless, of course, they were never separate to begin with. So, what is matter then, if not a collection of particles? It may be more accurate to think of matter as structured energy, patterns in the vacuum, shaped by fields, choreographed by symmetry, and perceived as stuff by minds evolved to touch and hold. We crave solidity, edges, objects. But nature offers none of these, only interactions, events, exchanges. Reality is not built from particles, it is woven from relationships. And yet, despite the abstraction, this illusion of matter works. It lets us build bridges, launch rockets, split atoms. The particle model is incomplete but profoundly useful, a story that, while not entirely true, is true enough to shape civilizations. Still, in the silence between quantum blips, in the mystery of entangled partners, in the impossibility of observing the thing itself, we're left with a haunting possibility. That the smallest pieces of the universe may not be pieces at all. The universe, as we perceive it, is composed of matter, stable, solid, dependable. Yet as we've peeled back the layers, the ground beneath our feet has shifted. The particle has dissolved into abstraction, mass has become conditional. And now, something even more disorienting emerges. Matter might not be fundamental at all. We're entering the realm of emergent phenomena, where the tangible, visible universe arises from something deeper, more elusive, more primal, and that something may not be made of matter, or energy, or anything at all in the conventional sense. To understand this, imagine watching a flock of birds, hundreds moving in synchrony, wheeling through the sky in complex patterns. It's tempting to think there's a leader, a blueprint, a signal guiding them. But no such thing exists. The beauty is emergent, a consequence of simple rules repeated across a system. Now imagine that flock is not made of birds but of quantum events, and the pattern they create is a proton, or a neutron, or the illusion of space itself. This is how modern physics is beginning to see matter, not as a fundamental ingredient, but as a behavior that emerges from a more abstract substrate, possibly information, possibly geometry, possibly something we don't even have a word for yet. Take space-time itself. In classical physics, it's a passive stage, but in quantum gravity, particularly theories like loop quantum gravity or ADS-CFT correspondence, space-time may not be fundamental. Instead, it arises from entanglement, from information networks, from the correlations between things, not the things themselves. If space and time are emergent, then so is everything they contain, including matter. There's a chilling implication here that the realness we assign to objects, atoms, and ourselves may be an illusion of scale, a mirage born from complexity, a pattern that feels solid only because we're part of it. In this view, an electron isn't a particle, It's a stable excitation in a deeper sea of potential, a ripple that persists because the underlying structure allows it to. Like a whirlpool in water, it looks like a thing, behaves like a thing, but it is not a thing, it is a process. Even mass itself begins to fall apart. The Higgs mechanism explains how certain particles gain mass through interaction with the Higgs field, a kind of universal drag. But not all mass comes from this interaction. Most of the mass of a proton, for example, doesn't come from the masses of its constituent quarks. It comes from the binding energy, the furious motion and tension inside the proton, held by gluons and governed by quantum chromodynamics. In other words, mass, that most thing-like property of matter, is largely an illusion too, not an inherent trait, but a byproduct of energy and confinement. We've been fooled not just by size, but by stillness. And then there's the vacuum. Empty space, we once thought, was a backdrop, a void. But quantum field theory paints a stranger picture. Even the vacuum boils with virtual particles popping in and out of existence, leaving measurable effects like the Casimir force or Lamb shift. The vacuum is not empty, it's pregnant with potential. From this seething nothingness, everything arises. So what do we call this level of reality, beneath particles, beneath fields, beneath space? Some physicists call it the Planck scale, a domain where quantum mechanics and gravity converge and where conventional physics breaks down. Others speak of a quantum substrate, or of pre-geometry, or even quantum information theory, where bits, yes, ones and zeros, are the true currency of the cosmos. One model suggests that everything, particles, forces, even space-time, arises from a kind of quantum computation, a cosmic code constantly executing itself. Under this lens, matter is no more fundamental than a JPEG file is to a computer. It's a pattern of instructions, rendered intelligible by the framework that runs it. This idea isn't science fiction. It's gaining traction in approaches like it from qubit, a view that the universe arises from entanglement and information, not from material ingredients. But if that's true, where does that leave us? If matter is not real in the traditional sense, if space and time are emergent, if particles are illusions of energy, then we are not beings made of stuff but of structure. We are not objects, we are relationships made flesh. This view is unnerving, yes, but it may also be liberating, because it suggests that the true nature of matter is flexibility, not rigidity. That the universe isn't built from dead things but from living processes, and that perhaps, just perhaps, the boundary between matter and mind is thinner than we think. After all, what is a thought but a pattern of energy across matter? What is consciousness but a ripple of awareness through a structure? If matter itself is emergent, then maybe mind is too, not separate but entangled in ways we don't yet understand. In the end, we may have been asking the wrong question all along. Not what is matter made of, but rather, why does matter appear at all? There is a quiet terror in realizing that everything solid is mostly space. Take a single atom, a nucleus, less than 1/10,000th the width of the atom itself, surrounded by electrons that behave more like clouds than orbits. If you were to scale up a nucleus to the size of a grain of rice, its nearest electron would be over 300 feet away. The rest, empty. And yet, from this emptiness arises everything we know: mountains, bones, machines, moons. The hardness of matter, the way a table resists your hand, is not from mass or solidity, but from electromagnetic force fields. A pushback, a resistance born from exclusion, not from contact. We don't touch things, we interact with their force fields. It is tempting to see this as reduction, to declare with cold pride that reality is nothing but math, fields, and vacuum fluctuations. But look closer, and something stranger emerges: coherence. Patterns that hold across vast scales, structures that should collapse but don't, relationships that persist through entropy's relentless erosion. How? Why? Some answers point to symmetry, the deep aesthetic of the universe. Every force, every particle, every equation seems born of a desire for balance, matter and antimatter, up quarks and down, spins that cancel, charges that conserve. The laws of physics are less about things and more about rules, and those rules often whisper of something more elegant than mere chaos. But not all symmetries survive. In the early universe, as temperatures fell, certain symmetries broke. Matter came to dominate antimatter. The strong and weak forces diverged. The vacuum settled into a shape that allowed particles to persist, and from that cosmic fracture, structure began. So if matter is the result of broken symmetries, what lies behind the break? Some physicists turn to supersymmetry, a proposed extension of the Standard Model that pairs every particle with a heavier shadowed partner. If true, it might explain dark matter, unify forces, and stabilize the quantum vacuum. But so far, no superpartners have shown themselves. Others look to string theory, where particles are not points but vibrating filaments, loops of energy whose modes of vibration determine their identity. In this view, an electron and a quark are not made of different substances, but are the same entity vibrating in different ways. But string theory does more than just rewrite particles. It demands extra dimensions, 10 or 11 depending on the formulation, curled up at every point in space. Entire universes, folded within the substructure of ours. If true, then matter is not just vibration, it is geometry. And then there is loop quantum gravity, which dispenses with particles altogether and treats space itself as quantized, made of discrete chunks, woven together like a network. Matter becomes the twist in the weave, a knot, a tangling of space-time itself. Each theory offers a glimpse of something deeper. None offer certainty. But one theme repeats: matter is structure, not substance, not solidity, structure. An organization of behavior across energy, fields, and space. A persistence of form, born from rules we barely understand. This idea echoes in condensed matter physics, where researchers study emergent particles, quasi-particles, that exist only within specific materials. Phonons, excitons, magnons. They have mass, momentum, even spin. But they are not real in the way an electron is real. They are collective excitations, illusions that behave as if they were particles. And yet, we can measure them, use them. They affect reality. What if all particles are like that? What if electrons and quarks and photons are the quasi-particles of a deeper substrate, one we can't yet access directly? What if our universe is not fundamental but emergent from a deeper layer of physics entirely? Some researchers have dared to suggest this, that reality itself is a kind of topological phase of a more complex quantum system, that we live in the low-energy effective theory of a much larger, more alien framework. If true, then matter is the shadow on the wall, the echo of a process occurring somewhere deeper, and what we call fundamental is merely local truth. And yet, it works. From the chaotic birth of the cosmos, matter organized itself into stars, then carbon, then life, then awareness. Somehow, through all the quantum weirdness, all the probabilistic haze, the universe built consciousness out of dust. How? Not by adding new particles, but by rearranging patterns. Your brain, your thoughts, your memories, they are not new matter. They are new configurations of old matter. That's what makes matter extraordinary, not its composition, but its capacity for self-organization. There is something profoundly humbling in this. We are not made of magic. We are made of hydrogen, oxygen, carbon, nitrogen, the same as trees, oceans, and stars. What makes us different is how that matter arranges itself, how it dances, how it remembers, how it dreams. And yet we are not apart from matter. We are matter. Which leads to the ultimate question. If matter is not fundamental, if it is made of energy or structure or information, then what are we really? Not just as observers, but as participants. Are we ripples in the code, emergent patterns in a vast quantum web? Momentary self-knots in space-time's fabric, asking questions before unraveling? What gives matter its meaning? Perhaps the answer isn't out there. Perhaps the final clue lies in the fact that matter, organized just so, begins to wonder what it is made of. In the end, what is matter? After centuries of crushing it, burning it, splitting it, and accelerating it into oblivion, the truth is not solid. It is not simple. It is not even entirely knowable. We began with the tangible, with things we could hold, break, shape, stone, metal, bone. The ancient world knew matter by its resistance. It was that which stood apart from spirit, from dream, from void. Matter was the real. But we now know that what we call matter is anything but. It is energy, confined. It is information, encoded. It is geometry, knotted into persistence. It is vibration. It is vacuum. It is potential, flickering on the edge of nothing. We have broken it down to particles and found only probabilities. We have sliced it with photons and discovered uncertainty. We have mapped its forces and found that the most powerful ones are invisible. At the smallest scale, there is no object, only behavior. At the largest scale, there is no substance, only structure. And in between, in this brief zone of temperature, pressure, and complexity where stars forge gold and carbon dreams of its own existence, matter arranges itself into a mind and asks why. Why should there be something instead of nothing? Why do these particles, these temporary flickering things, align just right to form molecules, to form cells, to form memories, to form the voice reading these very words inside your head? Why does the cosmos permit such exquisite precision, such fragility, such persistence? Some will say it is chance, that the laws were right, the dice were rolled, and here we are, a fluke of entropy, blinking in the dark. But chance alone cannot feel awe. It cannot reflect. It cannot ask what matter is made of, or whether anything is real at all. We speak of quarks and gluons, electrons and fields. We build colliders, supercomputers, equations that unfold across 10 dimensions. And still the question remains, is there a bottom? Is there a final brick, a last pixel, a core to the code, or is matter just the surface? A skin of appearance stretched over something stranger, something deeper, something we will never quite hold in our hands. The ancient Greeks believed the world was made of 4 elements: earth, water, air, fire. Today we know the periodic table. We know the quantum fields. We know in theory what makes a chair, a star, a breath. But the closer we get to the edge, the more we try to trap reality in a net, the more it slips through. Not because it's hiding, but because we are inside it. We are not observers standing apart from matter. We are the result of its deepest tendencies, our very thoughts, our questions, our doubts. They are matter in motion, matter imagining itself. And maybe that's the point. Maybe the universe never wanted to be understood from the outside. Maybe it needed a way to look in, not through formulas or instruments or theories, but through wonder, through the slow, trembling realization that the atoms in your hand were born in a dying star, and yet obey rules that emerged when there were no stars at all. Through the impossible fact that the same particles that form your bones once surged through the veins of supernova, then drifted silent for eons across the black before finding form again, as you. Through the idea that every question you ask about matter is a question matter is asking about itself. That is the final paradox. That is the final truth. What is matter made of? It is made of everything we do not yet understand. It is made of all the questions we still dare to ask. It is made of us. And when the last star dies, when the last atom decays, when the cold silence comes at the end of time, perhaps the only thing that will remain of matter is the echo of that question, still resonating in the dark. Why did I exist? Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern